Hello, 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 and welcome to tutorial number 50, the final one of the year, finally. So for this special occasion, I guess, we're going to look at fluid dynamics and how can we simulate them in Grasshopper. So we're going to use this little guy that's rotating on the screen as our test subject, and we're going to just see what kind of wind drag it makes in the wind tunnel. So there are options on what kind of software we could use, or rather what kind of plugins we could use. There's Rhino CFD and similar plugins to that, but all of them are quite expensive. So once we limit our budget to 0, because we like not paying money, we're only left with two choices, basically. A plugin called Swift and a plugin called Butterfly. Of course, both available for Grasshopper. Both of them are free, and I just decided to use Butterfly, so well, why the heck not, right? So this is going to be something a little bit harsher in terms of installing, and also it's going to be a little bit harder for me to explain what the different components do, but let's give it a try. So without any further ado, let us look at where you can get Butterfly. So again, as per usual in Food for Rhino, if you search for Ladybug tools and you scroll down, then here you can see there's Butterfly 0.0.05 release, which uses Blue Computational Fluid Dynamics core. So this is like open source core. Of course, Grasshopper in itself can't compute CFD models, so we need to use an external core, which makes installing of this kind of plugin a little bit more difficult than your usual Grasshopper plugins. So basically, you need to download this Butterfly 0.005. And also you need to go to this website here, that's listed here, github.com, Ladybug Tools, Butterfly Wiki. Once you open up that website, this is what you're going to see, right? And here you basically care about two links on this website. One is called Installing Blue CFD Core. So we open up that one. And the other one is Installing Butterfly. We open up that one. So in terms of Blue CFD Core, all you need to do is just blah blah blah, read through this, which can be downloaded from this page. You click on this link right here. You go deeper into GitHub basically, but you just need to download this little guy right here. And by little I mean 790 megabytes, whatever. You just download it, it's going to install, and you'll have the core available. The only drawback of this particular software, or this particular core, is that right now, since I have it installed, every time when I right-click my trash bin, it asks me would I like to open it in Blue CFD Core terminal, which I hate, but you get used to it. Other than that, it doesn't cost a lot. So let's come back here. So let's say you've installed the Blue CFD Core, then you just and you have Butterfly downloaded. Then you just follow the steps in the second link that we opened, called Installing Butterfly. You just follow those steps. You basically just run the installer.gh file, set it to true, and it's going to install. It's going to install the Butterfly plugin. Once you're done that, you're good to go, you're ready. So let's stop rotating. Why are you, oh, right, turntable. So then you just jump into Rhino. Let's change the view to shaded, and you get some sort of a mesh, or any kind of form. So here I'm using a Grasshopper to test out things and to test out how things are working, but basically you can just make a cube, right? Make a cube. If you want to be fancy, you can just Boolean difference out something from that cube, like that. and that's good enough for an initial test. Actually, yeah, let's do this later. Like, let's do the Grasshopper part later. Let's work with a cube first, right? So that all of you can follow along. So this cube right here, let me actually rotate it as well. This cube right here is going to be something that's placed in a wind tunnel, right? So it's inside of a wind tunnel, and wind is blowing along the Y direction, so along this green line, and it's creating some sort of a drag, some sort of a wind turbulence. You know, there's a lot of dynamics going on. We're going to simulate that and analyze that. Right, before we start, Butterfly works in meters, not in millimeters, so make sure that you go to units, enter, you type in units, you hit enter, you go to model units, and you change to meters. If you work in millimeters, it's going to be a mess, right? And in meters, the size of my cube is basically 11 meters high, 17 meters wide, 17 meters deep, right? So it's not a cube, of course, but this is just so that you know the basic sizes, right, of the thing. Then you open up Grasshopper and you start building up your script. So this is my notes. Basically, if I get stuck, I will take a look at them, and trust me, I will be taking a look at them because there's a lot of things that I don't necessarily know about Butterfly, but I do know the basics, and I'll try to guide you through them. So first things first, we need to reference in our box here, right? So let's do that. We will be using a node called geometry in this case, because I want to be able to reference either a brep or a mesh without having to do any kind of discrimination between the two types of geometries, right? So in this case, this is a brep, set one geometry, there we go. So geometry node, right? Perhaps I should do this, draw icons off, there we go. This should be better. Let me hide the geometry in Rhino, so that is only left in Grasshopper, and continue working with that. Let me just quickly check. Oh, I guess we can immediately go to... Yeah, we can immediately start working with within Butterfly. So here in the Butterfly tab, first thing that we do is we create a case for Butterfly to solve, right? So so basically we start from create tab and we find Butterfly create Butterfly geometry, I think. Or is it Butterfly create case from geometry? We'll see. Let's add both of them and we'll see which one is the correct one. Name geometry. Boundary. Okay, so it's not this one. It's not case from geometries, it's just create Butterfly geometry. So I'm going to delete that one. And for now, I'm just going to use create Butterfly geometry. So let's go through the inputs. It asks us for what kind of name will we give it. So I will just create a panel, // By the way, when you double click and type in // it automatically creates a panel. And it's waiting for us to give it some sort of a string, some sort of a, name, a text. So I'll just call this box version 1, box v1, and just connect it to the name input here, like so. There we go. Then for geometry, it's pretty straightforward. We just connect our geometry to the geometry input. That's nothing, nothing crazy. Then for boundary, it asks us for what kind of boundary does this geometry describe, right? So if I go in the top here, if I go to the boundary menu, I can see that it can be an inlet, it can be an outlet, it can be a wall. And in this case, of course, it's a wall. You know, these are series of walls. So that's my wall boundary. I'll just connect it like so. I wanted Christmas music. This is not Christmas music. Happy euphoric, no. We changed this. We changed this. Okay, so we have our geometry, that's a wall, and that has a name. Yeah. Refinement levels is basically, so all of this is going to be voxelized. So it's like meshed only in 3 dimensions. Yeah, it's going to be voxelized. So this is how small the voxels are going to be. So in terms of refinement levels, I need to, yeah, I can't see here. Let me just enable this part. Oh, okay, so it asks for 2 numbers, and that's 3. Okay, sure. So refinement levels basically asks us for when it's going to subdivide the voxels to fit better with the form here. What's the minimum amount of subdivisions that it should use, and what's the maximum? So in this case, we want it to be fast and kind of good enough, like precise enough. So we will create a panel, and we'll say the minimum is 1, comma, and maximum is 2, right? So basically wherever it doesn't have any, and let me just connect it to refinement levels, wherever it doesn't have any geometry, wherever the voxels are not intersecting with any geometry, it's not going to subdivide them, right? That's where level 1 of refinement lies. Level 2 of refinement, it's basically going to subdivide it once, I believe. I don't know how it works actually. It might be that 1 already subdivides every voxel and 2 subdivides it even further. But either way, we are using low numbers, which means we are trading off accuracy to more towards speed, and we do need to have a lot of speed here because unless you have an insane computer, it's going to run for quite a while. Number of layers for Snappy Hex Mesh, it's basically there's going to be another voxelization step involved later down the line, and here we will specify how many layers surrounding the shell here are going to have super dense voxels. So in this case, I will say 3 layers because I saw the default values were set to be 3. So I'm going to kind of stick to 3 layers. And mesh set, I'm just going to say, okay, what kind of mesh setting should we use for this one? I'll just say jagged. You know, setting speed. There we go. And that's it. That's it for this geometry. So it's basically what it did. It created this kind of a beefed up version of our box with a bunch of additional information, right? And it even has a report which probably will say nothing. Yeah, there's nothing. Of course, there's no errors. So then let me actually just turn this off and enable this so that I can see what's going on. Okay, so then once we have this geometry here set up, we want to put it in the wind tunnel, right? So the wind tunnel, oh, I believe it's as well, yes, it's under create, butterfly create case from tunnel, right here, I believe. Yeah, it should be. So butterfly create case from tunnel, we add that, which will ask for a name again. So I'll do / again, and I'll call this wind tunnel. I don't know. Oops. / wind tunnel. Like that. it's going to ask for BF geometry, and we have created it. So butterfly geometry goes in here. Right? That's easy. And it's going to ask for reference regions. So reference region is basically refinement region is basically a region in which the levels, the refinement levels are going to be amped up. So basically a volume in which the voxels are going to be smaller, thus having more resolution. So for ref regions, I believe we need to create it. Butterfly refinement region, there we go, this guy right here. I'm just going to double check. Yes, it is that. And this one is going to be, oh yeah, inside outside. Okay, so it's refinement region, and it's going to ask for a name. So again, I'm going to / and call it space around the box, so that it's more clear to you what this is, right? And I'll just connect refinement region into here, and it's basically asking us for geometry. And we don't want to just give it geometry like so, that wouldn't work, because we want the surrounding area, right, of this box, not the box itself necessarily. So what we can do, well, this is a little bit shitty. What we can do is we can create a bounding box around this geometry, like that. It would make more sense to rotate the bounding box, but I don't really care that much. So let's keep it as it is, like that. And we will scale this bounding box, but not uniformly, but rather as with non-uniform factors. And the reason why we're using this instead of, or wait, maybe we can just use scale. Yeah, let's just use scale instead, sorry. Let's use scale, so we're going to scale the box. And we're going to scale it not around its center point, or rather not around the 0, 0, 0 point, but rather around the bottom center point. Not the center point, but bottom center point of the box. The reason behind that is we don't care what's happening underground, so we don't need a lot of resolution there. So we're going to be scaling from the floor, from the center of the floor, if that makes sense, right? So to get the center point that is at the bottom of the box, we will use evaluate box component. Oops, like that. And we will just say U and V stays the default values 0.5, and W is 0. This is 0. Or maybe I should just make a slider. Yeah, like that. W is 0. So then the point is right here in the bottom, and we're Gucci. So we can use that now. And for scaling factor, you can use whatever number you want, as long as it's higher than 1. I will say 1.2. So slightly larger box surrounding our shape. And this is a region in which a higher refinement is going to take place. Cool? Cool. Okay, let me make this a little bit more tidy real fast. This is not tidy at all, but it will do. Yeah. Okay. So refinement mode, and actually let me hide everything except the scaled version. So this is, again, the box in which more voxels are going to be created. Refinement mode, I don't even know. I believe it's here. No, it's not here. Is it in boundary? No, it's not. That's calculated. Just give me a second. That's not here. No. Refinement region is this one. Meshing parameters, make 2D, block mesh. Okay, I need to check my notes. What are you? Where are you? Oh, it's a script. Do I need to use the script here? Because I borrowed the script from the example file. Let's see if we need it. If not more else. Okay, let's try working without the refinement mode. It should be fine. Or we can do distance. Can we do distance refinement mode? Let's try. Will I get demonetized for this music? No. No, we're not risking that. Okay, back to here. So let's try distance refinement mode. Okay, let's use location refinement mode rather. Yeah. So there are a few bugs here and there. Apparently, it is a part of the plugin. It's just when I try to check where it comes from, it will show me Python script, which doesn't make a lot of sense, I guess. But it is what it is. Either way. Or rather, it makes perfect sense. It's just unfortunate that it does that. Okay, so location refinement mode, let's add it here, and level. I believe we use 2, right? At least we use 2 here, so I'll use the same number. And then for mesh settings, Grasshopper mesh settings, should we use jagged again? Yeah, let's use jagged. There we go. So that is done. So this is part 2. Let me group this. This is part 1. This is part 3, and part 3 is still on its way. Okay, so we have finished refinement, and we basically are just saying that again, inside of this box, have more resolution of second level. So basically, if let's say our voxels are 1 meter by 1 meter by 1 meter, second level of refinement would be 0.5 and then 0.25, so 1/4 of a meter by 1/4 of a meter. So basically every voxel becomes 8 voxels no, not 8, sorry, 4 times 4, 16 times 4, 64. Every voxel becomes 64 voxels in that particular region. Okay, wind vector. So for wind, I don't remember where it is. Yeah, there we go. Create butterfly wind vector. We just create it here, plug it in. And for wind speed, we just say, by the way, speed is in meters. So we just say, yeah, 10 meters per second. Pretty fast. For wind direction, let's say, well, by default, it's set to be along the y-axis, which is right here. And I think we will keep it, right? So the wind is going to be going along the y-axis. Referenced wind height is 10, we don't care. Landscape. So landscape is basically how much of a wind velocity does the landscape eat up. So in this case, let's say it doesn't eat up any wind velocity, so we will use a number 0. Actually, let me double check if we need to add anything. No, we don't. Okay, that's good. And then we have 2 more inputs. So make 2D params, I have no idea what those are, so we skip through them. And tunnel parameters is basically the parameters for the wind tunnel. We will go to create wind tunnel parameters. There we go. Plug in tunnel params to tunnel params, that's easy. And here we just specify what kind of a size will our wind tunnel have. So this is a multiplication. It's multiplying the existing bounding box rather than the size of existing bounding box, rather than creating a new some sort of a box in which the calculation is going to be made from scratch. So these values right here are going to be multiplications of this surrounding bounding box. So let's say, why doesn't it show us any points? I want to show you. Oh, okay. So before we add anything here, let's create a button to run this, or a toggle to run this script. Toggle, boolean toggle, connected, toggle true. There we go. So these 8 points are created, and they basically describe an area in which the calculation is going to be made, right? So you can see it as a bounding box. I can even make a bounding box and show it to you. Box. Oops, that one, and right click on it, union box. There we go. So this is an area in which the calculation is going to be made, and I think it's way too big. So windward scaling should be less. I will say 1.5. There we go. That's closer to the box. Then top scaling should be definitely less. Let's try 1.5 as well. Well, maybe 1.5 is a little bit too little here. Let's try 2. Like that. Perfect. Sides X, leeward X. So sides are going to be these gaps here, and leeward is going to be, the tail. The rest of the box. So sides 1.5 I think will do the trick. Yeah, that seems okay. Leeward also let's just do let's do 2 for leeward. How much is it by default? By default it's 15. Okay, so let's do like 5. Yeah, that seems reasonable. So that we can see the whole draft going on there. Okay, that is done. This is running. Let me just group this part and give it a color. Like that, perfect. Do we need to see the union box? No, we don't. That's good enough. So this is, let me group this whole part. This is our wind tunnel created, and more importantly, a case from our wind tunnel created, right? So we can continue working on by creating what's called a block mesh. Which is going to be the voxelization part itself, right? So up until this point, nothing was voxelized, nothing was subdivided into these small cubes in which the calculations are going to be made. And this guy right here is going to do that. So it's going to ask for a case, and I could give it right now. Should I? Yeah, let's try. I'll give it a case here. and it's going to ask me to give it grading, right? So the voxels themselves are not going to be the same size, of course. They're going to be graded. For me to give it grading, I need to, I believe, go to Mesh, which is right here, and find Butterfly Wind Tunnel Grading. This guy right here, Wind Tunnel Auto Grading. That's perfect. So it's going to ask us for a bunch of things. I will give it a wind tunnel, like that. Perfect. Then it's going to ask us for cell size. I will say, so the cell size is the size of the voxel, I believe. Default is 1, which is 1 meter. I don't remember how much I used here. Yeah, I used the default, so let's keep it. Actually, I used all of these as defaults. Sure, let's keep it like that. Just know that this is the most important setting to change, cell size. Basically, if you want the script to be more accurate but run much more slowly, then you decrease the cell size. So again, by default it's set to 1, which is 1 meter, 1 by 1 by 1 meter. Either way, we get cell count 37, 45, 21. That's perfect. And we get, more importantly, we get the output grad XYZ. That's graded XYZ values. Let's see it like that. We connect it. It's hard to explain without any visuals here, but once we see the visuals, it's gonna look nice. Okay, so cell count, number of cells in XYZ as a point, default is 5. This value updates numbers of divisions and block mesh. We don't care, or maybe we do. Let's see if we do care. Oh, we can just connect it like that, of course. That's my bad. Cell count, XYZ, connect to cell count. Then overwrite, we keep it as true, and then it gives us 2 more inputs, write and run. So write, both of these are toggles. So write will write this information into an external file, a temporary external file. That's important. Run will take that external file and crunch the numbers with that open source CFD program that we've installed, so not with Grasshopper itself. So we need 2 toggles, like that, and we will toggle write to be true, and we will then toggle run to be true. And you can see that for a second there, command line was opened up, and it ran the script basically so it crunched the numbers, and now we have a output case, right? So it basically created those divisions. So it voxelized everything, well, to a certain extent. Let me group this and give it a color, because this is these 2 are important toggles. Okay, and let's group all of this as well. This is our step 4, I guess. Okay, so what are you? Tunnel parameters. Oh yeah, we already did that. Now we will do something that I don't necessarily know everything about it, but it's called Snappy Hex Mesh. So that's a fun name, but it's basically like a secondary refinement, I guess, of the voxels. So it kind of refines the voxels to be more precise. That's my best guess. So first of all, let's find where it is. It's under Mesh, Snappy Hex Mesh, right here. And actually you can see from the icons here, right? So these are the voxels, and Snappy Hex Mesh basically has more voxels surrounding some object, right? So it densifies the voxel grid, like that. Asks us for a case, of course, we give it. Asks us for location in mesh, and then a bunch of other inputs. So for this one, I do need to actually check what the hell is going on. So location in mesh, we don't need any inputs, that's great. Global refinement level, we don't need to add anything because we already gave it a refinement level right here, which is level 2. So we don't need to change anything. Then we have Snappy Hex Mesh dictionary, which, yeah, sure, let's just create a Snappy Hex Mesh dictionary, which is under, it's not under create, is it? It's under here, yes. Butterfly Snappy Hex Mesh dictionary. Like that. Connect, that's perfect. Then there's this decompose par dictionary. So do I even talk about this part? Really quickly. So there is this, where is it even? Are you here? Yes. So there is this decompose par dictionary Scotch, right? Which basically asks for how many CPUs do we use, and these are, I don't even know if these are CPU cores or if these are separate CPUs, but basically if you're running a render farm and you're doing CFD modeling through a render farm, then you do need to use this like that, and then connect, you know, oh, I have 180 CPUs, and then connect that slider, right, like so. But in this case, I'll just delete that and won't mess with that at all. Okay, so we have this guy almost ready, and it also has the write and run options. So let's go for toggle false, there we go. That's for write, and toggle false for run. Let me, as always, group them, give them a color, orange. Yeah, that's good. Group this, and let's run it. So first we write, we always write first, and then we run. And now it's going to do the actual legwork through this command line here, and it basically just explains everything that it's doing and so on. If this cmd.exe file doesn't open up for you, the command prompt file doesn't open up for you, then you can still, no, you can't. Okay, never mind. I thought that you could just hook up a panel to the report, but you can't. So you need to wait until it's finished. It usually takes a few minutes to do. If I were to check my CPU loads and so on, it's not necessarily running at full blast, right? So memory usage not that high, CPU usage definitely not that high, only 40%, doesn't go into turbo mode, so it's not perfectly optimized, but it is using all of the 12 cores that I have, which is great. And let's give it a second. Okay, so while it's doing that, let's see if we can change the music, because this is a little bit, or maybe it's enough of this Christmas music. Let's see what else we can listen to. What's this? Is this good? Or maybe let's listen to some hip hop. Okay. So it's doing the thing here. Okay, let me pause the video for a bit and then we will continue once it's done because it's taking too long. There we go. So we're back and it took it 4.5 minutes to calculate, but it's done now. So now we have a case that is ready to be solved, right? So everything is divided up and everything is good to go. So it's time to solve it, right? Let's go to create. No, it's not under create. Oh my God, now we need to, yeah, it's under solution. Of course it is. Butterfly solution. We will be using that. It will ask us for a case of, we do have a case here. It will ask us for a recipe, and the recipe, we of course expand the tab called recipe, and we will find either heat transfer or steady incompressible recipe. So we will be using the, let me just say the blue one. We will be using the blue one. And let's just connect recipe to recipe, and that's it. We will not be messing around with any inputs here. That's way too geeky, way too much. So we will be just using the default values. They seem to work, so let's not mess around. Again, the decompose does exactly the same thing as the decompose here. If you have too many CPUs, you can kind of specify that you have too many CPUs. Then you have solution parameters. So solution parameters are located here under solution, butterfly solution parameters. You have that input here, you connect it to solution parameters like so, which asks us for 1, 2, 3 inputs: control dictionary, probes, additional parameters. I don't remember what those do. Let me check. Control dictionary is just dictionary, and probes are of course probes for actually measuring the values that we will get from the solution output. So I'll explain more about it once we get there. So for control dictionary, let's see where it is. It's not here, it's probably under solution. Yeah, under solution, it's butterfly control dictionary. We just hook it up like so. We don't change anything. Start time, end time, and time step 1000. That's a lot. Let's do 100 just because this is a tutorial and I don't want to wait that long. Write interval, it's 100, so that's fine. Write compression, purge write, yeah, everything else is whatever. So end time 100. To run a decent simulation you need around 500, but again we don't want to wait that long. Probes. For probes we find butterfly probes. It's under solution as well. We just connect it like so. It basically asks for points, fields, or right interval. We only care about points. Wait, I do need to give it. Okay, yes. So we do care about points and fields. So points are going to be points at which we measure the wind direction and the intensity of the, not the wind, the air, right? The direction and the intensity or the speed of the air at different points. So we will need to create a grid for that. And then we have fields, which is U, P, or K. If I remember correctly, U is, if we give it the letter U, capital U, it is going to give us vectors. so basically direction plus strength. If we give it the letter P, it's only going to give us just the strength value. So connect U to fields, and for points, we need the surface. And I believe I do have a surface here, show selected. Yes, I do. I do have a surface here, which is right here. And I'm not going to mess around with its placement, but basically just create a surface like so, something like this, and reference it in srf as a surface. Set one surface, bam. Then we will, let me hide it, we will divide that surface into U and V values. So for U, I will use, in this case, I want it to go fast, so I'll use like 50. And for V, I will use 100. Something like that. So it's 5,000 in total. Let's do 4,000. No, let's do 3,000. Yeah, something like that. 30 by 50 by 100. So we have a bunch of points. I will flatten the output of P, right? So all of the points are flattened out now. And I will get rid of the points that are inside of my shape because I don't care about them. So I will ask in mesh or mesh inclusion, I will ask whether or not the points are inside or outside of this mesh right here. So mesh to test is going to be this guy, but oh, this is a brep, not a mesh, so I need to mesh it first. Let's just do it the fast way. Connect it like so, mesh. When you connect a brep to a mesh component, it automatically meshes it, the more you know. And I'll just drag it all the way to here. So this is the mesh in which we're checking. These are the points, we connect them like so. And is it strict or not, we don't care. So now we have a bunch of inside-outside statements. And if I use those statements to cull pattern, to cull the points with those statements, I'm left with only the ones that are inside of the box, but I care only about the ones that are outside of the box. So I need to right click on the P input of the cull and choose to invert the statements. So what was true becomes false, what was false becomes true. And now I get all of the points that are outside of that box in that particular area. Okay, so we have a bunch of points here. Let's move them a little bit back. And those are the points at which we probe, at which we measure, right? Okay, so once we've done that, this is all good to go. Then we still have three inputs here. Interval, that's going to be how often does Grasshopper show us the output. So I will say every 10 seconds. That's our interval. Right is going to be, yeah, as per usual. That's going to be a toggle. Run is also going to be a toggle. So for now, I'm not going to turn it on because, well, maybe I'll turn on the right, but I will not turn on the run. Because for me to run it, I want to kind of see something here, right? So I will say, give me the solution, and what kind of output do I want to get from solution? Load probes value. So solution goes in here. Field. So we are using field U. I will be checking for that //U, oh, capital U, like that. And it's going to complain, but that's normal because we are not running the. Jesus Christ, this is so bad. We are not running the solution, so it's not receiving any values. Maybe I can do that again. Ah, there we go. So now it's null, and now it's going to be red. Not sure why it's red. We will see if it's going to make a mistake. We will check once we run it. But basically here we will get vectors, right? And to display those vectors, I will be using vector display X component, which basically asks us for a bunch of points and vectors to display. So our points are going to be the points from which we probe. So these culled points right here are going to be our points, and vector to display are going to be the values from here. So I'll just hook up these values to a vector component, like that, and these vectors are going to be the ones that are going to be displayed. And then we have color. I actually want to color those vectors, so I'll use a gradient. Right click on the gradient, choose a prettier gradient, connect it like so, and I will just say, okay, so let's say there are different lengths of vectors, so I need to measure the length of the vectors, like that. And the ones that are short are going to be red, the ones that are long are going to be blue, or other way around. The ones that are long are going to be red, the ones that are short are going to be blue. So I will say, give me a domain. No, shit. Range. No, not range. I keep forgetting the name of it. Bounds. Give me the bounds. You know, the minimum and maximum values that I get from the lengths. So these are the bounds, and deconstruct this domain. Deconstruct this domain to start and end. And basically then I'll just hook up the end to L0 and start to L1, meaning that I'm flipping the domain upside down, so the long vectors are going to be red. And for my parameters, I'll use the vector lengths, like so. Oh, that's a lot of wires, I know. Let me try to make it as clear as possible. There we go, like that. Should be good to go. We save the definition and we just run it, don't we? We just run it. Double click. So now it's going to start calculating, and we will see if this is going to stay red. If it's gonna stay red, I will need to pause the video to check why is it red. No, it's not red, but it's the values that we get are empty. Why are they empty? It's not empty anymore. Yay! So you can see all of the vectors that are being calculated here. And it's basically going to run for quite a while, right? It will actually for 100 steps. And then once it's done, it's done. Cool? Cool. I don't know why it's not updating that often. Maybe it will update every 10 frames or something like that. It should be updating every 10 seconds. Not sure what's up with that. But it is working, right? And we are seeing some values going on here. Let me turn off the simulation now. And this is what we get so far. It's nothing too special, and actually the vectors are a little bit too intense. So let me let me unitize the vectors. So all of the vectors have the length of 1 and show them like that, so that it's more like a grid. And now you can see better what's going on, right? I think that's cool. I think that's cool. Of course, it's not three-dimensional in this sense. We need much more planes for it to be three-dimensional, but it's a good start. Okay, let's do it with the Grasshopper. Show. Let's get rid of the box and hook up the Grasshopper there. So before we do that, I will turn off all of the, goddammit, how are they called? All of the toggles, just so that it doesn't immediately start calculating everything. And actually, let's group the last toggles here. That's for the solver. And now I will set one geometry, set my Grasshopper in here. It's gonna take a little bit of time. Now it's all set. I will run the first toggle, or actually let's check this. Refinement Region, let's see the box. So the box is here. This is how, and here I'm using 1.25, that's even larger. Okay, so that's fine. So we create wind tunnel, we toggle through. 3.3 seconds, that's good. Let's hide this. Or rather, no, show. We show this. We hide this surface and we hide the shape itself. Okay, so this is true. Now we write it and we run it. Done. 2.2 seconds. Then we write the Snappy Hexagon Mesh and we run it, and it's gonna take a while, so I will pause the video and then we will continue once it's done. Okay, and we are back. So it took 7.1 minutes to complete, so that takes a while apparently, but we are going through this. So now what we need to do is we need to solve for the solution, right? Just like we did with the box previously. So there are two things that I need to change here. The first one is the end time, right? I want this to be a little bit more precise in terms of the computation itself. So instead of having end time set to 100, I will give it a little bit more time to converge. So I will try 200. I think around 500 would be the ideal end time for something like this, but we don't want to wait that long. Okay, so we have that going on. And then the other thing is the resolution, right? So you can see the resolution here in the cull. These are all of the points that are going to be measured. And also why? Oh yeah, that's fine. So these are going to be all the points that are going to be measured and evaluated. And I'm going to increase the resolution, I think, twofold. So instead of 100, we'll have 200. And instead of 30, we will have 60. Just to save some time, because this will take a while to calculate, I will disable this node here. And then I will plug in my new sliders to U and V values, delete the old ones, and then run the mesh inclusion check. The reason I'm doing this is because when I plug in the sliders, I plug them in one by one, and if you do it one by one, that means that mesh inclusion will calculate, will solve for the sliders one by one. So instead, what we want to do is we want to solve for them, both of them immediately or at the same time to just save some time. Either way, now we have twice as much resolution. It's still not perfect here, but that's fine. That's good enough, I think. All right, let me disable the cull so that we don't need to see it. We have our values here, which are null at the moment because we are not running anything. And we have our vector display. So let's see if there's anything else I want to change. So this will update every 10 seconds. I think we can go for... Shall we go for something lower? Let's go for 7 seconds. Or maybe let's go for something larger. Let's go for 20 seconds. Just to give the computer a little bit more time to not converge, but to calculate and not waste a lot of time trying to show us the output. Maybe 20 is a bit too much. Let's go for 15. Okay, so as per usual, we toggle this to true, right? So it shows something like this, which is definitely not, not good, but it hasn't started solving, so that's reasonable. And we'll toggle this to true as well, which is run. And now it's going to begin the calculations. This will take quite some time. I think it's going to be, we are running 200 steps, so it's going to be like an hour to calculate. So what I'm going to do is I will hide my webcam and I will make this as pretty as possible so that you can see a sped up version of this whole thing being solved. So first things first, I will minimize the Grasshopper window. I will look at it in the right hand side view like that. Should we... Oh, it's now calculating. Just give me a second. There we go. So I will zoom in to make it as nice as possible. I will change the display color, the background color of the display to black. Just something like this. And yeah, I think that's good enough. Let's make this as small as possible, larger. Like that. Perfect. So now I will disable my webcam. Like that. And I will just let this run. Okay, so there we go. So that didn't take too long. I think around half an hour, maybe 40 minutes. So I could have done it in a higher resolution or made more steps. But just as a proof of concept, I think this is good enough. One thing that you will notice is that it's not actually color coding the vectors that well. And the reason behind it is that there are a few vectors that make a, let's call it an error, right? That are not that accurate. So if I were to check the vector length bounds, let me just grab a panel and just show it to you. So the bounds are between something that's quite close to 0 and something that is an extremely large number. So this isn't like trillions. So that vector is nonsensical, right? It doesn't make any sense. So we need to kind of get rid of them, get rid of those vectors here and ignore them. And the way we do it is by just measuring. So here we have the vector length measurements, and we just say, is it smaller? Are these lengths smaller than, let's say, 100, right? Anything that is larger than 100 should be dismissed as nonsense, right? So then we get the answer, true and false. Like for every vector, it's either true or false. Is it smaller than 100? And with those values, we just cull pattern. We cull all of the lengths. So that's the list that we cull with this pattern. So basically we get rid of all of the vectors that are way too large. And then instead of just the pure vector length, we plug in cull into the bounds like that, and immediately it colors it. That's all we needed to do. And now, just to make it a little bit more nice, maybe let's change the preset here. That's 4 colors. I just need 2 colors. There we go. 2 colors for a preset. So the stronger the vector, the brighter it is. So we can kind of mess around and see. You know, we can see what kind of drag we get, and also, of course, we can color code it any way we want by just right-clicking on the gradient circles. I don't know how to call them, circle things, and just changing them up. Something like that. Well, maybe that should be actually bluish. Let's go for blue, and that should be red. Like that. And then somewhere in between, I don't remember how to add. How do you add? Yeah, it doesn't matter. I forgot. Either way, this is what we end up with, this vector grid, and yeah, that's about it. That's how it looks like. So there are a few main things to note here. First of all, it's not a dynamic representation of the wind flow. If you want a dynamic representation, you would need to run a swarm through this. And I can do it quite quickly. If I were to just say show, give me that surface right here, I will just reference in the surface. That is not the surface. srf. There we go. Right click, set one surface. So that's done. Let me hide it again. And then I will say, give me the edges of the surface, like that. So we have 4 edges, and then using list length, or rather list item, I'll just get this edge of the surface right here. Oh, that's actually the first one on the list. Yay. Okay, so we have that going on, and then I will divide that edge to get a bunch of points on it. Let's say 100 points, like that. And I believe that should be enough for us to check if it's going to work. So basically I want to move these points along these vectors to simulate the wind flow. And these points should draw lines as they move. So I will need a loop for that. Loop start. I'm using Anemone for this. Loop end. There we go, we connected. I'm going fast with this because this is not a part of the tutorial. It's just something that I want to test out if it's going to work or not. So trigger is a button, number of iterations, let's go for 1 for now. Loop start, so we start with the points, the starting positions of the points, and all of them will move. Do they move by a fixed amount? I don't think they should. So we will need to move them along the closest vectors. So somehow these points, let's say point, there we go. So somehow these points need to find, let's say, 3 or 4 closest vectors to them and average out the direction of these vectors. How do we do that? Well, first of all, we change the music because this is way too... There we go. So we have our points here, and we have our vectors right here. So let me just grab a vector component and just bring it here so that it's closer. So we have our vectors here, and we actually need not just the vectors, but also we need the starting points, like the points to which the vectors are anchored, and these are the probe points that we used here. So I'll just grab a point component as well from here, drag it here, there we go. Whew. Okay, so this is going to be like a group, and these are separate points. So basically from each of these we will need to pull each of these points. No, that won't work. Let's think. Oops. There we go. So we'll use closest points component, CPs. We will search from each of these 100 points, initial 100 points. We'll search for, let's say, 3 closest points out of this list right here, like that. And we will end up with indices. So these indices right here, we will be able to use these indices to extract the vectors that are associated with these points. So we'll use list item for these vectors with these indices, and it should be 3 vectors. Yes, perfect. 3 vectors for each point, and then we need to get rid of the vectors that are too big again. So we will measure the length of these vectors. Where is it? Length vector length, there we go. We measure that, ask if it's smaller than 100, and we call pattern. So we use the smaller answer of the smaller as a pattern, and we call the vectors. Perfect. And now all we need to do is just need to get an average vector. Let's just check what kind of output we get. Perfect. Okay, so we do get an average vector of all of these. All right, and all we need to do is just move these points by the average vector, like so. They seem to be quite strong in terms of movement. And also that's way too many points. That's because this is a flattened list and this is not, so we flatten this one. And now this seems to be doing the trick. It's moving way too fast. So I will multiply. The whole average vector by 0.1 so that it's 10 times weaker than it should be. And plug it in like so. So this should technically work. Let's see. Let me hide everything except loop end start. Okay, so that kind of works, but we need more. Slider 100. Okay. It's kind of doing it, but it's not that great. I wonder if there's any missing points there that got stuck. No, there's not. Okay, so let's draw a line instead, just to see what kind of curves we will get. So this needs to record data. The matrix needs to be flipped. And we just draw a curve, interpolated curve through it. Insufficient interpolation points for a curve. Why is that? That is because the recording doesn't work. Let's try again. There we go. So it is interpolating. Let's see. Yeah, it's kind of doing it, but it's way too fast now. But it is doing something there. Okay, so we are getting there, but the thing is, I don't even know what that's doing. We are getting there, but the thing is that it's way too fast still. But other than that, I think it's great. Okay, so we will be using more neighbors, 5 neighbors. We will be using 200 points instead of 100. We will be not looking at the points themselves, only at the curves. What else? And we will not be multiplying the vectors. Or should we? Maybe we should. But it should be a much smaller value. So let's try 0.01, 10 times smaller than it was. Let's just run 100 iterations of it. There we go, now it's properly lagging. So, okay, so again, this is not a part of the tutorial. We will be finishing up just shortly. Let me just connect it to the panel. There we go. This definition, for those of you who are lazy and don't want to follow along, this definition is going to be available for the Patreons as per usual. We are done with the tutorials for 2020. Thank God, we finished with 50 of them. And hopefully I'm going to do more, much more in 2021. So let's let Grasshopper finish up here. Let's give it 200 iterations and just see how it reacts to the Grasshopper right here. Seems to be reacting quite well. Will you bounce? You kind of bounce, but it could be better. I think we need better resolution. but the flow seems to work. Okay. So we are done. Hope you enjoyed this one, and I will see you next year. Bye.